Okay. Good morning. Let us discuss about some of the problems based on the section modulus for various sections of the beam. Okay. So problem number 1. So this is the problems on the section modulus for various sections of the beam. Okay. So let us see a typical problem. A cantilever of length 2 meter fails when a load of 2 kilonewton is applied at the free end. If the section of the beam is 40 mm into 60 mm, find the stress at failure. So this is a typical problem. Let us try to solve it. See, let us write the given data. L equal to 2 meter, that is 2 into 10 raised to 3 mm. Okay. Now the given load, the load coming on the beam is equal to 2 kilonewton, that is equal to 2000 Newton. Okay. See, it is given in the problem that the section of the beam, the cross section of the beam is 40 mm by 60 mm. Right. Okay. So therefore width of the beam is 40 mm. Okay, and the depth of the beam is equal to 60 mm. So if we want to draw the diagram, typical diagram, it will be something like this. If this is a cantilever beam, the distance is 2 meter. Okay, now the point load is acting 2 kilonewton, which is applied at the free end. Okay, and if you want to draw the cross section, the cross section is 40 by 60. So this is 40 mm and this is 60 mm. This is the cross section of the beam. Right. Okay. Now we know that the section modulus for a rectangular section for a rectangular section we have done in the last class. Z is equal to BD square by 6. So you can just substitute the values. B D square divided by 6, we'll get the value of Z, that is the section modulus. something 24,000. Okay, now see the unit of section modulus. This is 1 millimeter, this is millimeter square, so it is equal to millimeter cube. So we are getting the value of section modulus. Okay, now let us calculate the bending moment. How to find out the bending moment? See, this was the given figure. This was the cantilever 2 meter, and this is a point load at the free end. Now maximum bending moment for a cantilever is at the free end, is at the fixed end, sorry, it will be always at the fixed end because the load is acting at the free end. So bending moment will be equal to load multiplied by the distance. So this fixed end will be carrying the maximum bending moment, because this fixed end will try to bend, this beam will try to bend, but the bending moment will be at the side where it is fixed. Okay, so maximum bending moment will be equal to W multiplied by L. L is the shortest distance, so W is given as 2 kilonewton, that is 2000 Newton, multiplied by 2 meter, that is again 2000 mm. So maximum bending moment you will get 4 into 10 to the power of 6 Newton mm. This is the bending moment which you are getting. Okay, now let us assume that sigma max is the stress at failure. So we have a equation, that is my bending moment is equal to sigma max multiplied by the section modulus. This we have already derived in the last few classes. Okay, so we want to find the value of sigma maximum. Sigma maximum will be equal to bending moment divided by the section modulus. If you substitute the values, moment is 4 into 10 to the power of 6, and section modulus we have done, that is it was something 24,000 millimeter to the power of cube. So sigma maximum you will get approximately as 166.67 okay Newton per mm square. So this is the unit for stress, Newton per mm square. So this is your answer, that is the maximum stress. Find the stress, that is the maximum stress at failure will be equal to 166.67 Newton per mm square. So I hope this problem is clear. Okay, now let us go on to the next problem. See a typical problem. A rectangular beam mm deep and 300 mm wide is simply supported over a span of 8 meter. What uniformly distributed load per meter the beam may carry if the bending stress will not exceed 120 Newton per mm square. So see here, the maximum stress is given in the problem, right? Okay, now let us draw this figure. If this is a simply supported beam which is carrying a UDL, the intensity of UDL W per meter, okay, and if the total length is equal to L, so the total force will be equal to W into L. So there is a symmetric loading, so WL by 2 will be the reaction at RA and RB. Okay, now let us write the given values. Depth of the beam is equal to 200 mm. Width of the beam B will be equal to 300 mm. Length of the beam it is given 8 meter. Maximum bending stress sigma max is given 120 Newton per mm square. Okay, so let us draw this rectangular section. It is given depth is 200 and width is 300. Okay, so what we can do, we can find out the section modulus. How to find out the section modulus for a rectangular section? BD square divided by 6. So 300 into 200 square divided by 6. We will get the value as something millimeter cube. Please check this value. Okay, so this is the value of section modulus which you are getting. Now once you get the section modulus, let us find out the maximum bending moment. We know that maximum bending moment for a simply supported beam carrying UDL, it is given by W into L square by 8. This we have done in the chapter SFD BMD, right? So here the length of the beam is 8 meter, so W into 8 square divided by 8 you are getting, right? So it is equal to, you are getting 8W, right? 8W Newton meter, because it is moment. If you want to go to millimeter, then it is equal to 8W into 1000 Newton millimeter. Okay, so it is equal to 8000 W Newton millimeter. Okay, now we know that as per the formula, we know that maximum bending moment is equal to sigma maximum multiplied by Z. Okay, so if we just substitute the value, we know the value of maximum stress. Okay, so M is equal to, from A you get it is 8000, W is equal to, sigma max was 120, and this section modulus, it was something, right? So you will get the value of W from this equation divided by 8000. So W is equal to, we are getting 30 into 1000 Newton per meter, right? Because it is UDL, so it is per meter length, intensity is per meter length, or you can write 30 kilonewton per meter. So this, for this loading intensity, the maximum stress is limited to 120 as it is given in the figure. For a UDL of 30 kilonewton per meter, the maximum stress in the beam will be limited to 120 Newton per mm square. Okay, gradually we will solve some more problems. Okay, thank you.